Swayam Prabha. Digital India. Educated India.
Okay, many of you were able to answer this. It is Vp times exponential of -1 or Vp divided by exponential of 1, or numerical value is 0.3679 times Vp. Okay, so if I mark one time constant over here, okay, this is T equals Rc. Maybe it's not to scale. I should redraw this a little better. Okay. Okay, so that's what happens, and here the value is 0.3679 Vp. Okay, now if I go to 2 time constant, it will be 0.3679 squared and so on. Okay. So it will be approximately 0.1353 and it will rapidly reduce. Now it turns out that after approximately 5 time constants or 4.6 time constants, it goes down to 0.01 Vp. Okay. T equals 4.6 Rc. Okay, we approximate this to 5 Rc. The point here is that it will never completely discharge to 0, because if you look at this function Vp exponential minus 3 by Rc, it will never become equal to 0. Okay, it becomes equal to 0 only when t tends to infinity. So in a finite time it never goes to 0, but it becomes arbitrarily small. Now how small you want it to be depends entirely on the context. Sometimes you may want it to be 0.1% of the initial value, that is 0.01 Vp. Sometimes you may want it to be 0.1% or even smaller. Okay, but this is a good number to remember. For the voltage to reduce to 1% of the initial value, you have to wait for 4.6 time constants. Okay, so many times the time constant is denoted by the letter tau, and for this circuit it is equal to Rc, and in 4.6 time constants it reduces to 0.01 Vp. Okay, any questions about this? So when the input steps from some value to 0, we know how to solve it. We have the homogeneous equation, and by solving the homogeneous equation, we get the output to be an exponential, and this is the zero input response also, meaning we have calculated this response for the period when the input is 0. Okay, so now let's get back to the other case. where we have R and C, okay, Vs, and the differential equation governing this is Rc dVc by dt plus Vc equals Vs. The right hand side is no longer 0. Okay. So again, I will not take arbitrary functions for Vs, but I will take something that jumps from 0 to Vp at t equal to 0. Okay. So this red stuff is Vs of t. So for t greater than 0, the right hand side of this is a constant equal to Vp. Okay. So now we already intuitively evaluated that it starts with a slope of Vp by Rc, and it will do that. Okay. It will do something like that. So now we also have to find a function that corresponds to this. Okay. So any idea what this function might be? What might be this function? Okay, so there are a couple of answers. One of the answers is Vp 1 minus exponential minus t by Rc. That's correct. In fact, we will derive it properly. Also, there is an answer saying positive exponential. I'm not sure what is meant there. If you mean that the argument of the exponential will be positive, that's not correct. Because if the argument of the exponential is positive, you will get a curve that is like this, right? So it will go on increasing, it will blow up. Okay, at t equal to infinity, it will become infinity. That's not the kind of function we have, as we have determined from intuition. Okay, so it turns out that we can very easily derive this, because we know the result to the previous one when the right hand side is 0 for the homogeneous equation. In a very easy way, we can reduce this to the homogeneous equation. Okay, so there are standard tricks in calculus that all of you are familiar with, I think. So let me redefine a Vc1, which is Vc minus Vp. Okay. Now please tell me, so Vp is a constant, so keep this in mind. So what will be dVc1 by dt? What is this going to be? If Vc1 is Vc minus Vp, what is dVc1? What is dVc1 by dt? So please tell me what is dVc1 by dt if Vc1 is Vc minus Vp. Okay. So clearly, if Vp is a constant, dVc1 by dt is the same as dVc by dt. Okay. So what I will do is, I will rewrite this equation in terms of the new variable Vc1. Okay. So first of all, dVc by dt is the same as dVc1 by dt, and if you see this, I have Vc minus Vp equal to 0 if I take Vp to the left side. So that is nothing but Vc1 equal to 0. Okay. So here Vc1, in terms of Vc1, this is a homogeneous equation with the right hand side to be 0. Vc1 is just a new variable I have defined. Okay. So while solving problems, you do this all the time, right? You define some variable in terms of other variables and substitute. In this case, I have defined Vc1 to be a variable Vc minus Vp. What I want to calculate for is Vc. So instead of that, first I will calculate Vc1, and from that I will calculate Vc. Okay. So if I do that and write the differential equation in terms of Vc1, I will get a homogeneous equation. Okay. So Vc1 would be of the form V0 exponential minus T by Rc. So Vc, if I turn around this one, Vc is Vc1 plus Vp. Okay. So Vc will be of the form Vp plus V0 exponential minus T by Rc. Okay. Is this fine? So this is the general form of the solution to this equation, which has Vp on the right side. Okay. So this is not a homogeneous equation, and the solution to this will have Vp. It will also have some terms like exponential minus T by Rc, which was part of the zero input response. Okay. And it has this constant V0, which we have to adjust based on the initial conditions. Okay. So what is V0 and Vp? First of all, Vp is the size of the step, right? Vp, the input jumps from 0 to Vp. Okay. So that is Vp, and V naught is just a constant. Okay. So previously here I said that Vc will be some V naught times exponential minus T by Rc. That will satisfy the differential equation. And we calculated the particular value of V naught by looking at the actual solution at t equal to 0. So V naught happened to be Vp in the previous case. Okay. In this case again we have to evaluate the value of V naught. We will do that shortly. Okay. So now we have to evaluate the value of V naught. What we will do is, I know that Vc of t is Vp plus V naught exponential minus T by Rc, and if I substitute t equal to 0, what will I get? What will I get if I substitute t equal to 0 in this function Vc of t? So clearly exponential of 0 is 1, so the answer is Vp plus V naught. Okay. Now what is the value of the function? Actual value of the function at t equal to 0, it is 0, right? That we know. Initially the capacitor has 0 volts, and just after the input step the capacitor still has a value of 0 volts. So this should be equal to 0, which means that V naught equals minus Vp. Okay, it is clear. So there will be arbitrary constants in the solution to a differential equation, because the differential equation in the general form could be satisfied for any value of this constant. But by looking at the initial condition, you will be able to find the particular value that satisfies it for that case. Okay, so in this case, this V naught equals minus Vp. So the actual solution to Vc is Vp minus V naught exponential minus T by Rc, or minus Vp, sorry, Vp minus Vp exponential minus T by Rc. Also frequently this is written in this form, Vp 1 minus exponential minus T by Rc. Okay. So if you look at the solution here, at t equal to 0, both are Vp and this cancels out, or inside this exponential will be 1 at t equal to 0, and you have 0. And as t becomes infinity, this exponential part becomes 0. So Vc of t will become Vp. That's what we see from our intuition. And it starts from Vp, starts from 0 and then exponentially approaches this Vp. Okay, is this clear? Any questions? So okay then, so we have looked at the RC circuit. It is governed by a differential equation. We have solved for it intuitively. We know what it means. Okay, that is very important actually. We have of course taken a special case of only constant inputs. When I say constant, it jumps from one constant value to another constant value. Okay. Now if it does that, what happens to the capacitor voltage, and we will see later that this happens to every variable in the circuit, is it undergoes some change with some exponential argument, and the argument inside will be minus t by RC or minus t by some time constant. Okay. Now we solved it for zero input, that is, you have some initial condition and the input then jumps to 0. We also solved it for you have 0 initial condition and it jumps to some value. Okay. So let me just tabulate the results. The circuit we are looking at is this. RC, and the variable I am trying to calculate is this. I took two kinds of inputs. One where the input jumps from some Vp to 0. Okay. And in this case, the capacitor voltage Vc will do something like that. Okay. And the other case was where the input jumped from 0 to Vp and the output, it turns out, does something like that. Okay, this is Vc of t, Vc of t. So this corresponds to basically a 0 input. And in this case, we have a 0 initial condition on the capacitor voltage. Okay. Now the capacitor voltage is also known as the state. A capacitor can hold some voltage, so that is known as the state of the capacitor. So this is also known as 0 initial state or 0 state. Okay. So the differential equation governing the 0 input circuit is that the important thing here is that you have terms containing Vc and its derivatives, and the right hand side is 0. Okay. So this is known as the homogeneous equation. And in the other case, the differential equation is Rc dVc by dt plus Vc equals Vs. And we are talking about constant values of Vs or Vp. Okay. And the solution to the 0 input case, it turned out, was Vp exponential minus t by Rc. Okay. And the solution to this case is Vp minus Vp exponential minus t by Rc. Okay. So we will look at these expressions and classify them into different parts. Okay. It turns out that this part is called the forced response. This is the natural response. The entire thing is the 0 state response in this particular case, and this is the 0 input response. We will look at all of those things in the next lecture. So if you have any questions now, I will clarify them. Any questions about any of this? RC circuits and differential equations? Okay then, I will see you on Thursday. Okay.